In this video, we'll look at example 5 of your nuclear physics lecture notes. So for this example, you're asked to consider this following reaction, and you're also given the masses of the nuclei in the above equation, and these are the masses of the reactants, and these are the masses of the products. So the first part of the question, it asks you to find what is the mass loss by the system in the nuclear reaction. So since it is mass loss, this means that the mass of the products, this must be less than the mass of the reactants. So to find the mass loss, we simply take the mass of the reactants and then we subtract from it the mass of the products. So the values here will allow us to find the mass of the reactants, and from the values here we can see that to find the mass of the reactants, we simply need to just add them together. So that will be 2.014102U plus 14.003074U. So I'm going to work in U, don't convert at this moment, and that will sum up together to be 16.017176U. Next, I'll find the mass of the products. So the mass of the product would be the mass of carbon-12, which is 12.000000U plus 4.002602U. And putting this into the calculator, I will have 16.002602U. And we can indeed see that the mass of the reactants is actually larger than that of the mass of the products. And now we can find the mass lost in the nuclear reaction. So what you can do is put in these two values. I'll leave you to substitute and then work out together. Put this into the calculator and you will be able to get the answer to be 0.014574U. Now the question does not require me to convert to kg, so tentatively I'm going to leave this as the answer for part A. Okay, so let us now go to part B. So in part B, you are asked to find the equivalent energy lost by the system, and you want it in mega electron volts. So what we're going to do is I'm going to first find it in joules, then convert it to mega electron volts. To find the energy lost by the system, so what I need to do is convert the energy, convert the mass that we found earlier to energy, and we're going to draw on Einstein's mass energy equivalence, and that will be E equals to mc squared. And the mass here, I'm going to substitute in, would actually be the mass loss that we have calculated in part A. So that would be 0.014574U. But to find the energy in joules, I need to convert this into SI units. So I need to convert this into kg. So I need to multiply by 1.66 times 10 to the power of minus 27 to convert this to kg. Now I can put in the speed of light, c squared, which is 3.00 times 10 to the power of 8 meter per second. And remember to square this. Put this into a calculator. I should be able to get this in joules. But I want it in mega electron volts. So I will need to convert this value into mega electron volts. So 1 electron volt is equals to 1.60 times 10 to the power of minus 19 joules. So what I need to do is I can divide this whole value by 1.60 times 10 to the power of minus 19 joules. And then 1 mega electron volt is actually 1 times 10 to the power of 6 electron volts. So working this out, you should be able to get the value to be 13.6 mega electron volt. And that would be the answer for part B. Okay, now moving on to part C. In this part of the question, you are asked to find or asked to comment what is this lost energy manifested as. So if this reaction does not have any other byproducts, often after the reaction, both your carbon and helium will be moving away from each other. So they would possess kinetic energies, all right, because they are moving away. And so the lost energy is often manifested as the kinetic energy of the products, that is, the kinetic energies of both carbon-12 and the helium-4 nuclei. Lastly, in part D, you're asked to suggest why the combined energy of the products are usually higher than that of the value calculated in B. So this would mean that the total energy, if it's conserved, there could be some other forms of energy. And where could that come from? This is most likely from the initial reactants. This is because for the reaction to occur, you must first bring your hydrogen 2 and nitrogen 14 together. So what you will need to give it to them is kinetic energies so that they can collide together. And so often your nitrogen 14 is often bombarded with the hydrogen 2, so that there is already some kinetic energy before the reaction. And since the total mass energy initially is larger, hence by conservation of mass energy, the total mass energy is larger as well. And then the combined energies of the products would be usually higher. This concludes example 5.